Okay, so here we are with Lesson 8, Unit 3. This is the first part of using if-then moves in solving equations. So a lot of this is going to be a review, but again, just more experience with different situations. So recall from Module 2 that the process for solving linear equations is to isolate the variable by making zeros and ones. In this module, the emphasis will be for us to rewrite an equation using if-then moves into a form where the solution is easily recognizable. The main issue is that in later grades, equations are rarely solved by isolating the variable. For example, how do you isolate the variable for an equation that is 3 times x squared minus 8 equals a negative 2 times x? Instead, we will learn how to rewrite equations into different forms where the solutions are easy to recognize. So, recall the following if-then moves from Lesson 21 of Module 2. First, the addition property of equality. If A equals B, then A plus C equals B plus C. The second one, subtraction property of equality. If A equals B, then A minus C equals B minus C. And the third one, multiplication property of equality. If A equals B, then A times C is equal to B times C. And the last one, division property of equality. If A equals B and C is not 0, then A divided by C is equal to B divided by C. So go ahead and take a look at the opening exercise, complete it, and then continue the video to check your answers. Okay, so the first part just had you recall what we just went over, just stating the four properties of equality using the operations. Then for the second part, and again your answers will vary, but they asked you to write as many true equations as you can using the if-then moves and identify which if-then move that you used. So here are just some examples, adding 4 to both sides of this equation, or subtracting 4, or multiplying each side by 4, or dividing each side by 4. You could have picked different numbers and the numbers could have changed throughout. So this is just some examples. Alright, so the rest of this lesson is going to be all about examples, so we're just going to step through these. But again, seeing if you can predict what you think is going to happen in each step. So example 1 on your lesson worksheet, we have 3 people who are volunteer firefighters and they are collecting money. We have Keller who collects $42.50 more than Julia, and Israel had collected $15 less than Keller, and the total that they collected is $125.95. So based on this information, how much did each person collect? And we're going to start off with a tape diagram. So in order to represent this, Julia, Keller, and Israel all have at least in part the same amount of money. And this is based on the fact that Julia, we don't know how much she has made, but Keller has $42.50 more. So what ends up happening is to show that Keller has $42.50 more than Julia. They all start out with Julia's amount. And then Israel, it is described that Israel collected $15 less than Keller. So that means that it's $42.50 minus $15, which leaves us with $27.50. So in total, all 3 of them collected $125.95. And so here's our tape diagram to model this. So basically we have 3 units, which we don't know about, plus the $42.50, plus another additional $27.50, and that equals $125.95. So as you simplify that down, that becomes $70, and then 3 units is equal to $55.95, because we can subtract that. And then the last part is dividing by 3 to get that. The first unit is $18.65. So arithmetically, what we could do is we know $42.50 and $27.50 is equal to 70. So this part right here. And we would subtract that from $125.95. And then we would divide by 3 and get $18.65. So that's how you guys would probably normally do this without using any algebra. So what operations were used to get our 1 unit of $18.65? Well, to summarize, we add $42.50 and $27.50. Then we subtracted that from the total and finally divide it by 3. All right, so now switching to a more algebraic way, let's say the amount of money Julia collected is J dollars. So write an expression to represent the amount of money Keller collected. Well, again, if Julia collected some amount of money and Keller collected $42.50 more, then we would represent that as the expression J plus $42.50. Well, then for Israel, he collected $15 less than Keller. Well, if this is representing Keller, then we would take this and subtract the $15 from it, or simplifying it, we'd have J plus $27.50. And then using these expressions, J being for Julia, J plus $42.50 for Keller, and J plus $27.50 for Israel, all three of these equal $125.95. So now, solving that equation, we can simplify. We get J and plus J again, so that's where the 3J come from, the any order, any grouping. And then we have our constants here, the $42.50 and the $27.50, that equals 70, and it equals our total. Well, then using our if-then move, subtracting $70 from both sides, we get 3J plus 0 equals 55.95, which is any grouping, and using the additive inverse right here, which the additive identity would mean that we are doing 3J equals 55.95. And then here is where you can branch off if you don't want to multiply by the reciprocal of 3, which is 1/3. You can show that you are dividing by 3, which is essentially the same thing. So since they're going by the associative property and multiplicative inverse, that is where you get 55.95 times 1/3. Or again, you can do 55.95 divided by 3. So for J, being Julia, that means that she collected $18.65. Then using that information, that means that Keller collected $61.15 and Israel collected $46.15. So going ahead and just looking at this while we're discussing it, how does a tape diagram translate into the initial equation? Well, again, each unknown unit represents how much Julia collected, and that's what we're calling J dollars. So the initial step to solve the equation algebraically is to collect all the like terms on the left-hand side of the equation using the any order, any grouping property. And then the goal is to rewrite the equation into the form x is equal to a value or a number by making zeros and ones. So how can we make a 0 or 1? Well, again, that is going back to our properties of equality. Zeros are made with addition. Notice it doesn't say subtraction, because what is the definition of subtraction? It's adding the inverse. So that's why they only mention addition here. And then ones are made through either multiplication or division, depending on how you want to go about that. So we can make a 0 by subtracting 70 from both sides, or we can make 1 by multiplying both sides by 1/3, or dividing by 3. Both are correct if-then moves, but if we start by making 1 by multiplying or dividing, then we're going to end up with actually extra calculations. So that's why we always do the order of operations backwards. We start by adding and subtracting first, and then finishing up by multiplying and dividing last. So let us subtract 70 from both sides. The if-then move of subtracting 70 from both sides will change both expressions of the equation, both left and right sides, to the new non-equivalent expressions, but that the new expression will have the same solution as the old one did. So we're changing them, but they are going to equal each other in the end. So in subtracting 70 from both sides, what do A, B, and C represent in the if-then move? If A equals B, then A minus C equals B minus C. Well, in this case, A represents the left side of the equation, 3J plus 70. B represents the right side of the equation, which is $125.95. And C is representing 70. And remember, we're going to subtract 70 from both sides. So continue to simplify the new equation using the properties of operations until reaching the equation 3J equals 55.95. Can we make a 0 or a 1? Well, we can make a 1 by multiplying both sides by 1/3, or again dividing by 3, whichever you prefer. Since we are assuming that j is a number, that makes the equation 3 times j equals 55.95 true. We can apply the if-then move of multiplying both sides by 1/3 or dividing both sides by 3, and the resulting equation will also be true. So how is the arithmetic approach, the tape diagram with arithmetic, similar to the algebraic approach solving an equation? Well, the operations performed in solving the equation algebraically are the same operations done arithmetically. So we used addition or subtraction, and we used multiplication or division, again, depending on which way you wanted to go. So how can the equation 3j plus 70 equal 125.95 be written so that the equation will contain only integers? What would that new equation be? Now, you might say, well, we already have integers, except here we have a rational number because of the decimal point. So what we could do is we can multiply each term by 100. That means the equivalent equation would be 300j plus 7,000 equals 12,595. Now each term is an integer because we have effectively gotten rid of our decimal point by multiplying by 100. Well, this is still going to yield 18.65 or 18/6500ths, because if you go about subtracting 7,000 from both sides, you get 300j equals 5,595, and when you multiply by 1/300th or divide it by 300, whichever you do, you're still going to end up with the decimal 18, or mixed fraction if you want to call it that, 18/6500ths or 18.65. So what if instead we used the amount Keller collected, K dollars? Would that be okay? How would the money collected by the other people then be defined? Well, it would be okay, since Keller has collected $42.50 more than Julia. Then that means Julia would have $42.50 less than Keller. And Julia's money would be K minus $42.50. Since Israel's money is $15 less than Keller, then Israel's money would be K minus 15. The expressions defining each person's amount differ depending on who we choose to represent the other two people. So complete this chart in your math journal to show how the statements vary when the variable x changes. So if you notice, since we started with Julia, and we write this in terms of Julia's amount, then Israel would be j plus 2750, and Keller would be j plus 42, and that should be 0.50 also. Well, let's say we start with Israel. What if Israel was the beginning amount? Well, Julia is $27.50 less than Israel. Notice how it is the exact opposite. There is still this relationship here between Julia and Israel. If we start with Julia, then Israel made $27 more. If we start with Israel, then Julia made $27 less, or $27.50. And in this case, Keller would be $15 more. And for Keller's amount, if we started with K for Keller, then Israel would make $15 less than him, and Julia would make $42.50 less than Keller. So notice how, and these should actually be the same because this should be $42.50. It's missing the 50 cents here. But these two are related, Julia and Keller, because if you notice, J and K are related too. So notice the relationships between each of these expressions depending on who you start with. The amounts between the people are either added or subtracted from the other person. So let's take a look at example 2. You are designing a rectangular pet pen for your new baby puppy. You have 30 feet of fence barrier, and you decide that you would like the length to be 6 1/3 feet longer than the width. Draw and label a diagram to represent the pet pen. Write expressions to represent the width and the length of the pet pen. So here is where drawing a diagram would be very, very helpful. So if we know that the pen is going to be 30 feet all the way around, we know that the width is going to be some number and that the length of the pen is going to be 6 1/3 feet longer than the width. So here's where we can use a variable to represent the width, and then the length is represented by the width plus the additional feet. So find the dimensions of the pet pen. Well, using this arithmetically, we would do 30 feet minus 6 1/3 minus 6 1/3. And then divide it by 4, because now we would be back to 4 equal lengths. Well, 17 1/3 divided by 4 is 4 1/3. So if the width of the pen is 4 1/3 feet, then the length would be 6 1/3 feet more than the width, which means that the length would be 10 2/3 feet. So algebraically, if we go back to our drawing, we would do x plus 6 1/3 plus x plus 6 1/3. And again, most of you would recognize that we could do 2 times x plus 2 times the quantity of x plus 6 1/3, and you can by all means start like that. Eventually you will get to this part right here. 4x plus 12 2/3 equals 30. And then by using our if-then move, subtracting 12 2/3 from each side, we would end up with 4x equals 17 1/3, which is the same thing as right here. And they decided to multiply by the reciprocal, which is the reciprocal of 4 is 1/4. And you do that to both sides, and you would end up again with x equals 4 1/3. So if the perimeter of the pet pen is 30 feet and the length of the pen is 6 1/3 feet longer than the width, then the width again would be 4 1/3 feet, and the length would be 4 1/3 plus 6 1/3, which is 10 2/3 feet. All right, example 3. Nancy's morning routine involves getting dressed, eating breakfast, making her bed, and driving to work. Nancy spends 1/3 of the total time in the morning getting dressed, 10 minutes eating breakfast, 5 minutes making her bed, and the remaining time driving to work. Well, if Nancy spends 35 1/2 minutes getting dressed, eating breakfast, and making her bed, how long is her drive to work? So we're going to write and solve this problem using an equation and identify the if-then moves used when solving the equation. Well, let's say the total time of the routine takes x minutes. So if 1/3 of x plus 10 plus 5 is equal to 35 1/2 minutes, then that means that 1/3 x plus 15 equals 35 1/2 minutes. And so by subtracting 15 from both sides, we get 1/3 x plus 0 equals 20 1/2. And then multiplying by the reciprocal of 1/3, which is 3, we would get 3 times 20 1/2, which is 61 1/2 minutes. So 61 1/2 minus 35 1/2 equals 26, and therefore it takes Nancy 26 minutes to drive to work. So is your answer reasonable, and explain? Well, the answer is reasonable because some morning activities take about 35 1/2 minutes. So the total amount of time for everything will be more than 35 1/2 minutes. Also, when checking the total time for all the morning routine, the total sum is equal to the total time found. However, to find the time for driving to work, a specific activity in the morning, it is necessary to find the difference from the total time and all of the other activities. So let's take a look at this. What does the variable x represent in the equation? Well, x represents the total amount of time of Nancy's entire morning routine, again minus the driving. So explain how to use the answer for x to determine the time that Nancy spends driving to work. Well, since x represents the total amount of time in the morning and the problem gives the amount of time spent on all the other activities besides driving, the total time spent driving is the difference of the two amounts. Therefore, you must subtract the total time and the time doing the other activities. So let's model this arithmetic approach with a bar model. Notice that 1/3 of the total time is spent dressing, and that's 1/3 of the total time for the whole thing. So if you mark this as the whole thing and divide it up into 3 equal parts, then this 1/3 of the time is for dressing. Well, then out of this next part, 5 minutes is for making the bed, 10 minutes is for eating breakfast, and so dressing, the bed, and breakfast, that total time is 35.5 minutes. Then the rest of the time, this extra part here from the second third and this last third here is going to equal the driving time. So getting dressed represents 1/3 of the total time. We know the other morning activities take 15 minutes, the 5 plus 10, and therefore part of the bar is drawn to model the 15 minutes. So we know that the bar represents the time getting dressed, and the other activities of 15 minutes equals the total time of 35.5 minutes. So that's this right here. Therefore, the getting dressed bar is equal to 35.5 minutes minus the 15 minutes. So that leaves us with 20.5 minutes. So the dressing part is 20.5 minutes. Well, the remaining bar that represents 1/3 of the total time is also 20.5 minutes. So this next part right here is 20.5 minutes, and this last part right here is 20.5 minutes. So if we have 3 of those, 3 times 20.5 minutes would be 61.5. So the time spent driving would be equal to the total time less the time spent doing all the other activities. So 61.5 minutes for this whole thing minus the 35.5 minutes is going to leave 26 minutes. So 26 minutes is left for driving. All right, so for example 4, the total number of participants who went on the 7th grade trip to the Natural Science Museum consisted of all 7th grade students and 7 adult chaperones. 2/3 of the total participants rode a large bus and the rest rode a smaller bus. If 54 of them rode on a large bus, how many students went on the field trip? So let's take a look at an arithmetic approach. We know that we have, again, 1/3 on a small bus and 2/3 on a large bus. So we start with a total tape diagram that we split into 3 parts, three equal parts as best as that we can. Well, we know that 2 of these parts, because it said 2/3, is going to be equal to 54. And we know that out of this last part, we have 7 people who are adults, and that means that we have this last part here that we don't know about. Here is 74. So we know that the total amount of students is 74 students. So total on both sides of the bus, or on both buses, is 54 divided by 2, because we have, again, 3. 54 divided by 2 and then multiplied by 3 because we have 3 bars here. So the total number of students is 81 minus 7 is equal to 74. So 74 students went on this field trip. Because again, if we have 2/3 that rode the large bus and 1/3 on the smaller bus, that means that we have 81 total people, but 7 of them are adults, so that means the leftover is 74. So the algebraic approach, we know that we had the number of participants, which is the number of students plus 7 adults. Well, 2/3 of the total participants is equal to 54, which means that in order to get rid of this 2/3, we can multiply by the reciprocal. Well, if we multiply by the reciprocal, that would be 3/2, which means we have to multiply this side of the equation by 3/2, and this is where we get 3/2 of 54. So now this means that we get 1, and 1 times the quantity of s plus 7 equals 81. S plus 7 equals 81, which means now our next step is to subtract 7 from both sides, and that's where we get s is equal to 74. So 74 students went on the field trip. Again, take this algebraic approach and compare it to our tape diagram and arithmetic approach and see where the relationships lie between these two approaches. So how can the model be used to write an equation? Well, by replacing the question mark with s, we see that the total number of participants is s plus 7. And since the diagram shows that 2/3 of the total is 54, we can write 2/3 of s plus 7 is 54. So how's the calculation 54 divided by 2 times 3 in the arithmetic approach similar to making a 1 in the algebraic approach? Well, dividing by 2 and multiplying by 3 is the same as multiplying by 3/2. So which approach do you prefer and why? Well, hopefully you said the tape diagram in this problem is harder to construct than usual, while the equation seems to make more sense. And even though neither one of them make complete sense, hopefully you can at least start to see the relationships between the two. So for our closing and summary, see if you can describe how if-then moves are applied to solving a word problem algebraically. And comparing the algebraic and arithmetic approaches, name the similarities between them. Which approach do you prefer and why? And how can equations be rewritten so that the equation contains only integer coefficients and constants instead of fractions? All right, we'll see you in class.